Science, Space, and Technology will come to order. Without objection, the chair is authorized to declare recess of the subcommittees at any time. Good morning and welcome to today's hearing entitled The Future of Fossil Energy Technologies Leading the Way. I now recognize myself for 5 minutes for an opening statement. This morning, we will examine the status of the early stage research performed by industry, nonprofit institutes, and the Department of Energy, national laboratories to enable advancements in fossil energy technologies. Global demand for fossil fuels will hold steady in the near term and is projected to increase far into the future. Our abundant natural resources, including coal, oil, and natural gas, can and should be produced to meet this demand. However, these fuels should be utilized with efficient technologies that minimize the environmental impact. Early-stage research funded by the federal government, coupled with efforts to develop new technologies by the energy industry, are critical to ensuring we can use our resources long into the future. Over the years, this partnership between the labs and industry has led to the development of advanced scrubber technologies to significantly reduce the release of NOx, SOx, and other unwanted byproducts from fossil-based power plants. Because of this technology-led success today, we can often focus on another byproduct of fossil power production, that being carbon dioxide. But unlike other emissions, carbon dioxide can potentially have a number of key uses in industrial applications. As our knowledge in chemistry advances, so does our ability to capture and repurpose carbon waste as an industrial product. These utilization technologies have the potential to convert carbon dioxide into building materials or even reuse CO2 as part of the power generation cycle instead of steam. Because of the potential benefits to this technology, industry is investing in research to advance carbon utilization. This industry engagement has advanced independently of any federal regulation and combines private sector investment and the tools and technical assistance provided by national labs, state research facilities, as well as universities. Early stage research in the national laboratory system also supports the development of new energy production technologies. An example, at Lawrence Livermore National Lab, researchers have developed a 3D printed polymer that uses bacteria to convert methane, the primary component of natural gas, into methanol at room temperature and pressure. This technology has the potential to reduce any methane leaked from natural gas production by cost-effectively capturing and converting it to liquid methanol at small scales. This research, led by the national labs, can now be taken up by industry to improve the extraction and efficient use of natural gas products. This partnership is a win-win for science, for energy, and for the environment. However, in recent years, the use of our limited taxpayer research and development dollars has kind of shifted away from fundamental research like this to the support of large-scale technology demonstration projects, one that the industry has the ability to fund on its own. Welcome. The research community and the private industry would be better served if we focused federal investment on the early stage research that has a proven track record of producing transformative energy technologies. I want to thank our panel of witnesses for their testimony today, and I look forward to hearing what role Congress should play in advancing fossil energy research. I now yield to the ranking member, Mr. Reese.
Thank you, Mr. Chairman, for holding this hearing, and thank you to the witnesses for being here today. Fossil fuels currently account for about 60% of our electricity generation in the U.S., and they will likely continue to command a large market share of this for decades to come. Power plants are now the second largest source of greenhouse gas emissions, just a bit behind the transportation sector. Reducing these emissions and finding technology solutions to these realities is a very pressing challenge. It's going to require stable public investment in our academic institutions and national labs, alongside significant partnerships with the private industry. That is why in May I introduced H.R. 5745, the Bipartisan Fossil Energy Research and Development Act of 2018. I was joined by my colleagues, Mr. McKinley from West Virginia, and our committee's ranking member, Ms. Johnson. This bill would authorize critical activities within DOE's Office of Fossil Energy. This office is responsible for stewarding research to reduce emissions, improve efficiency, and mitigate the environmental impacts of energy generation from fossil fuels. A large portion of this research focuses on developing carbon capture technologies and demonstrating the use and storage methods for the captured CO2. H.R. 5745 would authorize and expand research, development, and demonstration of these technologies for power plants, including large-scale pilot projects that would fill a vital gap in DOE's current portfolio of projects in this area. The bill also authorizes R&D activities in carbon storage, rare earth elements, and carbon utilization, which I understand we'll hear more about from Dr. Aines shortly. It also supports significant improvements in efficiency, including the development of supercritical CO2 technologies, which I know we'll hear more about from Dr. Brun this morning. In addition, the bill would launch important new initiatives in carbon dioxide removal, methane leak detection, mitigation, and carbon dioxide pipelines. And finally, it would put in place key reforms to DOE's Fossil Energy Lab, the National Energy Technology Laboratory located in West Virginia and Oregon. Authorizing these technologies would also benefit the environment, our economy, and potentially provide technology solutions to global partners aiming to cut emissions. The critical work authorized in this bill is supported by a diverse array of stakeholders, including representatives from industry, academia, labor, and environmental organizations. Two major U.S. coalition groups representing a large group of interested stakeholders on these issues. The Carbon Utilization Research Council, represented by its director, Ms. Angielski, is here today, and the Carbon Capture Coalition have endorsed this bill. And without objection, Mr. Chairman, I would like to submit this letter of support for the bill from the American Federal Government Employees Union for the record.
Without objection.
In closing, I'd like to strongly encourage all of my colleagues on the committee to consider co-sponsoring H.R. 5745, and I look forward to discussing the best ways we can move these technologies with this excellent panel of witnesses that we have today. And Mr. Chairman, I yield back the balance of my time.
Thank you, sir. Now I recognize Mr. Biggs, Arizona. Chairman.
Okay. Thank you, Mr. I forgot you going.
Thank you, Mr. Chairman and Mr. Chairman. Good morning and welcome to today's Joint Environment Subcommittee and Energy Subcommittee hearing on fossil energy technologies. I thank our witnesses for being here. I look forward to hearing their interesting testimony today after reading their submissions. Today we will discuss cutting-edge fossil energy technologies that will both advance our nation's environmental interests as well as maintain American energy dominance. Like it or not, power generated by fossil fuels is and will continue to be America's core source of base load electricity. Unfortunately, due to regulations and media-garnered negative public perception, the fossil fuel industry is under constant attack. Moreover, these regulations result in more economic harm than environmental gain in the way of job loss and higher utility bills for hardworking Americans. Today's hearing will focus on technologies that, when commercialized, can both boost the economy and clean our air for generations to come. The reality is that there is no reliable and affordable alternative to fossil fuel-generated power at this time. As a result, fossil fuels will continue to support economic and infrastructure development, both here in the U.S. and abroad. As we learned from our recent hearing on climate adaptation, a strong economy and reliable infrastructure is necessary to protect against potential environmental harm. Shuttering a coal power plant in Arizona will not mitigate the effects of sea level rise in California. That effort requires advanced building materials and a reliable grid, all things made possible by fossil fuels. The question remains, how do we balance the apparent need for fossil fuels with a call for lowering the amount of carbon dioxide in our atmosphere? We do that by incentivizing the creation of technologies that capture the carbon before it leaves the power station and developing innovative ways to use that captured carbon for commercial purposes. Those technologies known as carbon capture, utilization, and sequestration, or CCUS, present a win-win for America. Rather than be emitted into the atmosphere, CCUS gives us the opportunity to convert carbon dioxide into a useful commodity. Not only do these technologies allow for the continued viability of the existing fleet of fossil fuel plants, but they create the prospect for new industry sectors altogether. While the federal government certainly plays a role in foundational research in this area, the private sector is best situated to innovate and scale up these technologies. One example we will hear more about today is the Wyoming Integrated Test Center, or ITC. The ITC is a public-private partnership that has received no federal funds. Located at the coal-powered Basin Electric Power Plant outside Gillette, Wyoming, the facility is set up as a testing site for researchers to scale up technologies designed to convert carbon dioxide into commercially viable products like building materials and plastics. Facilities like the ITC are why America is the leader in CCUS technology. As the production and demand for fossil fuels continue to grow worldwide, it is essential for Congress to continue to encourage innovation in this area. Again, I thank the witnesses for being here. I look forward to learning more about their interesting work and in the government and the private sector. With that, I yield back.
Thank you, sir. With the chair, I recognize the gentlelady from Oregon, Ms. Bonamici.
Thank you, Mr. Chairman. Our nation is facing a serious confluence of factors affecting our energy policy: a growing global demand for energy, a heavy reliance on fossil fuels, high energy prices, and climate change resulting from harmful emissions. In 2015, the Energy Information Administration found that fossil fuel usage accounted for nearly 82% of all energy consumption in the United States. This was the lowest share in the previous 100 years, but still demonstrates our dependence on fossil fuels. The dangers to our climate and environment from the carbon emissions generated from fossil fuel production and use have been studied and confirmed. It is more important than ever that we develop a comprehensive national energy policy that includes a greater emphasis on investing more, not less, in research and development programs to improve efficiency and reduce emissions to keep our air and water clean. In Oregon, we are leading the nation to decrease our reliance on fossil fuels with our robust renewable energy portfolio of solar and wind resources. By focusing our investments on renewable resources, we not only protect our environment, but we also have the opportunity to support new industries, new jobs, and innovative small businesses that are developing clean energy technologies. During the transition, and for states not making similar commitments yet, fossil fuels must be used in a responsible way that mitigates environmental harm. The Department of Energy's Office of Fossil Energy supports research on ways to reduce the negative environmental effects of using and developing fossil energy resources. This includes improvements to the efficiencies of a wide range of fossil and non-fossil fueled power plants through the advancements of technologies such as supercritical carbon dioxide power cycles. Much of this cutting-edge research is conducted at DOE laboratories, including the National Energy Technology Laboratory, NETL, in Albany, Oregon. The lab is also advancing affordable carbon capture technologies that reduce emissions and use captured carbon dioxide to increase domestic oil production from depleted oil fields. Despite these innovative efforts at the Department of Energy, this administration has sent inconsistent messages about fossil energy technologies. President Trump has highlighted the need for clean coal and has worked to bolster fossil industries, but has simultaneously attempted to slash funding for the critical federal research supported by the Office of Fossil Energy in his fiscal 2019 budget request. As a result of strong collaborative efforts between federal and non-federal partners, the U.S. is considered a leader in the development of various innovative fossil energy technologies, such as carbon capture and storage. Underfunding these activities could ultimately cede American leadership in the rapidly developing low-carbon economy. As members of the Science Committee, we should be encouraging the Department of Energy to continue supporting unparalleled research into environmental mitigation strategies for fossil fuels that would otherwise not be pursued by the private sector. Until we regulate carbon emissions in the U.S. to drive innovation in the private sector, government-sponsored research is critical to fill the gaps in the market. Through these investments, there is tremendous opportunity for the U.S. to promote a healthier environment and become a leading exporter rather than importer of the next generation of fossil energy technologies. I'm pleased to see a well-rounded witness panel today to discuss the successful partnership between federal, state, and private sector researchers in this field. I look forward to learning more about current technologies used to mitigate the environmental effects associated with the production and use of fossil fuels and the innovations that can support a new national energy policy. Thank you, Mr. Chairman. I yield back the balance of my time.
Thank you, Madam Chair. Now recognizes the chairman of the full committee, Mr. Lamar Smith of Texas.
Thank you, Mr. Chairman. Energy produced from fossil fuels is abundant, affordable, and vital to America's security and competitiveness. As global demand for fossil fuel energy increases, America is on tap to become a net energy exporter. The research done at Department of Energy National Laboratories is vital to increasing the fossil fuels efficiency and reducing environmental impacts of this vital power source. Basic science discoveries at DOE National Labs have led to a range of technological innovations used by private industry in fossil energy production and fossil power systems. From horizontal drilling and hydraulic fracturing to improved sensors and geologic mapping, we've seen dramatic improvements in fossil fuel production technology that was developed from research conducted in the DOE lab system. For example, field engineers today are using augmented reality and virtual reality technologies in maintenance, operations, and exploration of reservoirs. Using this technology in the field can reduce the environmental footprint of energy production and increase oil and gas production as well. And in fossil power production, new approaches like the use of supercritical carbon dioxide power systems can replace the use of steam power, improving efficiency and potentially producing virtually carbon-free energy. The Southwest Research Institute, located near my district in San Antonio, is partnering with DOE to lead early-stage research efforts in developing these supercritical CO2 systems. In the past, the DOE's Office of Fossil Energy Research and Development programs focused primarily on reducing emissions from fossil power. While research on carbon capture, storage, and sequestration technologies remains a priority, there is also potential to research ways to use carbon as an energy resource rather than only considering it as a waste product. At the National Energy Technology Laboratory, DOE is funding basic research to create usable substances from carbon waste, such as concrete or plastics. If these techniques are commercialized by industry, they could provide added revenue for fossil power plants, making carbon capture a cost-effective method to reduce emissions. DOE's early-stage research should focus on developing a broad range of innovative technologies to improve the efficiency and effectiveness of fossil fuels, allowing us to use all our natural resources long into the future. I look forward to hearing about the promise of fossil energy technologies from our witnesses today and how DOE-funded research supports technological innovations that improve the efficiency, environmental impact, and safety of fossil fuels. And you'll yield back, Mr. Chairman.
Thank you, sir. Chair, now recognize the gentlelady from Texas, the ranking member of the full committee, Ms. Johnson.
Thank you very much, Mr. Chairman, and let me welcome our witnesses. I want to express my appreciation to both Chairman Weber and Chairman Biggs and our distinguished ranking members for holding this hearing to discuss the future of fossil energy. Certainly, we have seen how advances in science and engineering can produce large-scale economic value in this sector, and historically, our federal R&D agencies have played a major historic role in this process. Just over a decade ago, we had little idea of the fossil resources that would be available to us today. However, due to some critical research investments made by the Department of Energy over 40 years ago, coupled with rising oil prices in recent decades, the U.S. underwent the shale gas revolution that brought major natural gas resources online, and with it, a sharp increase in domestic oil production. That DOE program wrapped up in the early 90s when a private company took that federally supported research and used it to trigger the oil and gas boom we see today. I think my colleagues would agree that is the model for DOE's energy technology programs we all hope to see. Federal investment shepherding transformational technologies to the marketplace, even when the end point is not clear at the beginning of the process. That brings us to what should be the fundamental question we consider today. Where should the Department of Energy be investing its limited dollars in this area if the standard of identifying a federal role rests on whether the private industry has the capacity to invest in R&D? Then I think the answer to the question is that DOE should focus its investments on reducing and, wherever possible, eliminating the environmental impacts of the production and use of these resources. At present, there is unfortunately little incentive for industry to spend major R&D dollars to protect the environment, and even less incentive in the private sector to prevent the most devastating potential impacts of climate change. This is why I'm pleased to co-sponsor H.R. 5745, the Bipartisan Fossil Fuel Research and Development Act of 2018, which Ranking Member Vesey and Mr. McKinley and I introduced in May. This bill would reauthorize and expand important activities to develop and scale up innovative carbon capture, utilization, and storage technologies. It would also launch vital new initiatives on carbon dioxide removal and methane leak detection and mitigation, among other areas. In all likelihood, our society will continue to use and develop our fossil energy resources for at least several more decades. So these technologies will be absolutely critical to minimizing the harm they would otherwise cause to our public health and to the environment. Before I close, I would note that I am surprised that we are holding a hearing on DOE's fossil energy technology development activities without inviting DOE's Assistant Secretary for Fossil Energy to testify. It seems to me that it would be important for us to ask him to provide a better explanation for why the administration is proposing a 31% cut to DOE's fossil energy research and development activities. This is in stark contrast to the stated positions of the President, who has been praising clean coal and vying to end a supposed war on clean coal throughout his time in office so far. The rhetoric is not matched by the necessary resources, and this committee needs to know why not. So I hope that we will have Assistant Secretary Winberg before our committee to discuss these issues further in the near future. And I look forward to working with the administration and my colleagues on both sides of the aisle in the months ahead to steer a better course as we aim to accelerate the development and deployment of these next-generation technologies that could significantly improve our environment, our health, and our nation's economy. Thank you, and I yield back.
Thank the gentlelady. I will now introduce our witnesses. Our first witness today is Dr. Roger Aines, Chief Scientist at Lawrence Livermore National Laboratory, LLNL's Energy Program, and Senior Scientist in the Chemistry, Materials, Earth, and Life Science Directorate. Dr. Aines has been at LLNL for over 30 years, working on nuclear waste disposal, environmental remediation, and management of carbon emissions. He previously led LLNL's carbon management program, which takes an integrated view of the energy, climate, and environmental aspects of carbon-based fuel production and use. Dr. Aines holds a Bachelor of Arts in Chemistry from Carleton College and a PhD in Geochemistry from the California Institute of Technology. Welcome, Dr. Aines. I now recognize Chairman Smith to introduce our second witness.
Thank you, Mr. Chairman. It's a privilege to introduce Dr. Klaus Brun, the Machinery Program Director at Southwest Research Institute, located in San Antonio. Southwest Research Institute specializes in advancing science and applying technology to benefit government, industry, and individual American lives. Dr. Brun leads an organization of more than 60 scientists who focus on research and development for the energy industry. He is internationally recognized for his expertise in energy systems, power generation, and turbo machinery. Dr. Brun holds a Bachelor of Science from the University of Florida and a Master of Science and PhD, both in Mechanical Engineering from the University of Virginia. He is a Fellow of the American Society of Mechanical Engineers and the current Associate Editor of their Journal of Engineering for Gas Turbines and Power. Dr. Brun, we welcome you and look forward to your testimony.
Thank you, Mr. Chairman. Our next witness is Ms. Shannon Angielski. Okay. And the Executive Director of the Carbon Utilization Research Council, CURC. Prior to her current appointment, Ms. Angielski served as the Associate Director, do we pronounce that Kirk, CURC? Okay. She is a member of the National Coal Council, the American League of Lobbyists, and the Environmental Law Institute, and serves on the board of the Washington Coal Club. She earned a Bachelor of Art in Political Science and International Affairs from the University of New Hampshire and a Master of Science in Environmental and Public Policy from Johns Hopkins University. Welcome. Our final witness today is Mr. Jason Beggar, the Executive Director of the Wyoming Infrastructure Authority. Mr. Beggar, I understand your wife is very pregnant and due just almost any time. We appreciate you choosing to be here. I guess you proved that beggars can be choosers. So we'll see if she still lets you back in case that baby starts early. So we appreciate the prayers and blessings for that youngin's arrival. Prior to this, Mr. Beggar worked for 2 members of Montana's congressional delegation, focusing on Bureau of Reclamation water projects and Department of Energy Office of Fossil Energy Funding. He went on to serve as the Vice President of the Petroleum Association of Wyoming and then Manager of Government Affairs for Cloud Peak Energy. Mr. Beggar holds a Bachelor of Art in History from Montana State University, Billings, and a Master of Business Administration from the University of Denver. Again, welcome this morning. We hope you the best, you and your wife the best. So I now recognize Dr. Aines for 5 minutes to present his testimony.
I've submitted my full statement to the committee, which I asked to be made part of the hearing record. If I may, I'll now summarize in a brief opening statement. Thank you, Chairman Smith, Ranking Member Johnson, Chairman Weber, Ranking Member Vesey, and Chairman Biggs and Ranking Member Bonamici for this opportunity to share our insights into the current status and future of fossil energy and carbon capture, utilization, and storage. My name is Roger Aines. I'm the Chief Scientist of the Energy Program at Lawrence Livermore National Lab. I've worked on fossil fuel technology and carbon management for 20 years. At Lawrence Livermore Lab, we're focused on tomorrow's clean energy system. This testimony provides an update on emerging fossil energy technologies, including carbon capture, carbon storage, carbon utilization, and advanced energy systems, and finally removing carbon dioxide from the atmosphere. It includes an assessment of the current state of CO2 utilization in American industry. This current state foreshadows a future in which natural gas and CO2 become feedstocks for valuable products, just as was noted many times in the opening statements, creating an economic opportunity for all regions of the United States using our abundant resources and new technology. The mission of the Department of Energy's national laboratories is to advance science and technology that addresses issues of today, to anticipate pending national and global challenges, and help provide solutions to them in close partnership with companies that can bring those solutions to the market. The need for efficient fossil fuel technologies that can provide an engine for enhanced U.S. competitiveness has led to DOE research and analysis conducted at Lawrence Livermore Lab as well as other national labs. Today, technology is rapidly transforming fossil energy. But despite enormous progress in carbon capture, carbon dioxide is still not being managed in the power and industrial sectors because that is still too expensive. However, many businesses are eager to turn carbon dioxide into products. Turning a waste into a feedstock will help solve the cost problem. This is called carbon utilization, or I like to call it carbon recycling, and is poised to become a major industry. Last month in Livermore, we held a roundtable discussion with 20 corporations, ranging from Exxon to 3M to Nike, all who were interested in how they can improve their products with materials made from carbon dioxide. This is a ripe area for research, with much work going on today at university labs such as Stanford and Rice universities. This is an opportunity for new technology to aid multiple industrial and power generation actors who want to manage their carbon dioxide. New technology like 3D printing, as Mr. Weber mentioned, will be important to that transition. Natural gas will also be an important part of the transition to what we call the new carbon economy, where carbon-based products that we use every day are increasingly made from simple feedstocks like carbon dioxide, natural gas, and electricity. The chemical industry will be the first to be impacted by the ease of using them to make the fibers and plastics that are part of our lives. New industrial centers will spring up in places where carbon dioxide, electricity, and natural gas are abundant and cheap, such as the center of the country. An important innovation is combining biology with 3D printing. My laboratory works with the National Renewable Energy Laboratory to use engineered bacteria that they create, and we then 3D print along with a binder to actually make the reactor out of the bacteria. Natural gas flows in, and in our most advanced case, lactic acid, a valuable precursor for synthetics, flows out. The bugs do all the work. These kinds of new technology options will also allow us to address the challenge of removing the excess carbon dioxide from the atmosphere. A new carbon economy that values carbon dioxide as a feedstock and not a waste will help with this task. Much new science and technology development will be required and is just beginning today. The United States is poised to be the leader in the use of CO2 and natural gas for new carbon products, a new carbon economy. This will create new economic opportunity and improve national security as it makes us more energy self-sufficient. Development and demonstration of innovative fossil technologies will be the key to that process. Because energy and the necessary feedstocks, carbon dioxide and natural gas, are abundant in the central United States, we anticipate that new industries will thrive there. Both basic research and development and transfer of that research to corporate users will be important accelerators for the new carbon economy. That research and development done by national laboratories strives to bring that vision to fruition. Thank you very much.
Thank you, Dr. Aines. Dr. Brun, you're recognized for 5 minutes.
Thank you. Good morning, Chairman Smith, Ranking Member
I
Johnson.
want to turn on your mic there, please, sir.
Sorry. Good morning, Chairman Smith, Ranking Member Johnson, Chairman Weber, Ranking Member Vesey, Chairman Biggs, and Ranking Member Bonamici. My name is Klaus Brun, and I'm the Machinery Program Director at Southwest Research Institute in San Antonio, Texas. I'm honored to address you today on behalf of Southwest Research Institute. Southwest Research Institute, headquartered in San Antonio, Texas, is one of the oldest and largest independent not-for-profit applied research and development organizations in the United States. For the last 70 years, our mission has been to work in the public's best interest and toward betterment of mankind. Southwest Research Institute currently executes approximately $550 million in contract R&D per year and employs about 2,600 staff members in Texas and throughout the U.S. Cheap and reliable electricity is the cornerstone of our economy. The supercritical carbon dioxide, or SCO2 power cycle, has been a major collaborative development effort between industry, government, and research institutes to make electricity cheaper, more reliable, and also cleaner. For the last 250 years, the majority of fossil fuel power plants have been using steam and air. But technology development never stands still, and we must pursue the next improvement in power plants. The SCO2 power cycle is not a new energy source. It is a technology that incrementally but significantly allows us to make better use of energy from conventional fossil fuels and some non-fossil energy sources. SCO2 power cycles replace steam or air of a conventional power plant with carbon dioxide at very high pressures and high temperatures. Carbon dioxide is a common gas that is abundantly available, non-toxic, and easily handled. Due to the high density and high heat capacity and low viscosity of SCO2, plant efficiency gains of 3 to 5% are easily realized versus conventional steam plants. In industrial waste heat recovery, nuclear, and concentrating solar power, plant efficiency improvements of 10 to 15% over steam are possible. Waste heat recovery from thousands of currently underutilized energy streams in industry and oil and gas becomes technically feasible and commercially viable. SCO2 plants are about 5 to 10 times smaller than conventional plants and do not require water. That drastically reduces plant capital cost, reduces footprint requirements, improves plant grid response, and allows for siting throughout the United States. Finally, SCO2 technology provides a clear development path toward oxycombustion, which is a less expensive, higher efficiency, and completely carbon-free emission fossil fuel power plant technology. So why now? The thermodynamic advantages of SCO2 power cycles have been known since the early 1950s, but at the time, the manufacturing technology, the materials, and the design tools did not exist to produce SCO2 power cycles. Using advanced additive manufacturing, high temperature and high strength superalloys, and state-of-the-art computational engineering tools, all technologies that have only recently become available, we can now build the complex microchannel heat exchangers and ultra-high density energy compressors and expanders that are needed for SCO2 power cycles. These technologies are advancing at a very rapid pace, and we expect significant further benefits in efficiency improvements to power plants in the near future. SCO2 power cycles are on the verge of commercialization, and the U.S. is clearly the leader in this technology. A mix of nearly 120 government and industry projects with approximately equal R&D funding of about $500 million from government and $500 million from industry has allowed moving technology from concept stage to functioning plants over a short period of less than 8 years. Several U.S. Department of Energy offices and labs, including NEDL, NREL, EERE, ARPA-E, Sandia, Oak Ridge, have all constructively collaborated in this major cross-cutting effort. We are now working on an SCO2 pilot research facility called the Supercritical Transformational Electric Power, or STEP program, that is designed to help industry address pre-competitive development problems and demonstrate key cycle components. STEP is a $115 million DOE project led by Gas Technology Institute, Southwest Research Institute, and General Electric that aims to demonstrate 10-megawatt supercritical CO2 power plants. The STEP facility will be located at Southwest Research Institute in Texas and is scheduled to be operational by 2020. The STEP program and the many other industry and government-funded SCO2 R&D projects benefit the U.S. economy through the development of better power plants for cheaper, more reliable, and cleaner electricity for U.S. consumers. In my opinion, the SCO2 power cycle collaboration and cross-cutting initiatives between government, industry, institute, national labs, and academia is currently one of the most successful cooperative R&D programs in the world. Continued participation by DOE and other government agencies in these efforts will result in major benefits to the U.S. power industry as well as U.S. energy technology leadership. I sincerely want to thank the U.S. government, its agencies, and its employees who continue to passionately contribute to this very important work. I'm honored to have been invited to talk about this exciting technology to the congressional subcommittees on energy and the environment. Rarely does a new technology emerge that is capable of offering so many solutions. Thank you very much, and I look forward to your questions.
Thank you, Dr. Brun. Ms. Angielski, you are now recognized for 5 minutes.
Thank you, Mr. Chairman, and to the members of both the Energy and Environment subcommittees and to those committee members that are here today for the invitation to testify and discuss this topic with you. CERC is an industry coalition that is focused on technology solutions for the responsible use of our U.S. fossil energy resources to support our nation's need for secure, reliable, and affordable electricity through a balanced portfolio. CERC serves as an industry voice to identify technology pathways that will enable our nation to continue to enjoy the benefits of our abundant and low-cost fossil fuels in a manner that is both compatible with societal energy needs and environmental goals and objectives. Members of CERC work together to advance a common set of technology objectives that can be met through public and private sector collaboration, designed to expand technology choices for private sector commercialization. I want to recognize that the U.S. has already made significant strides in the development of advanced fossil energy resource technologies to improve the utilization of these resources. Similar to how a new car today, can travel further on a single gallon of gasoline than one that was built back in the 1980s. The most advanced coal units operating today are 25% more efficient than the previous generation of coal units. And this is a direct result of the public-private sector collaboration, which many of my members were involved with. As already recognized by many of the opening statements, consumption of fossil fuels is on the rise both domestically and internationally, and this trend is projected to continue well into the future. There's growing international consensus that technologies are needed to further reduce the carbon footprint from the use of fossil fuels. As a result, more recent efforts have focused on technologies to reduce carbon dioxide emissions. There is a first-of-a-kind carbon capture project successfully operating on a coal-fired power plant in the U.S. today that is selling its carbon dioxide to enhance recovery of oil in a nearby oil field. Many of you from Texas may know this project, the Petronova project. This innovative project relied on federal financial support to launch. And while research is advancing that will result in improved technologies, carbon capture is not yet economic for widespread application in the power sector, and further technology innovation is needed. Later this month, Kirk and the Electric Power Research Institute will release the 2018 Advanced Fossil Energy Technology Roadmap that, if implemented, projects new technologies can be available in the next decade by 2035 timeframe that generate electricity from fossil fuels with significantly reduced carbon dioxide emissions, and importantly, can be cost competitive with other sources of electricity generation. By way of background, EPRI conducts research, development, and demonstration projects for the benefit of the public in the United States and internationally. As an independent, nonprofit organization for public interest, energy, and environmental research, they focus on electricity generation, delivery, and use in collaboration with the electricity sector, its stakeholders, and others to enhance the quality of life by making electric power safe, reliable, affordable, and environmentally responsible. EPRI does not advocate or aim to influence policy or regulation. This will be the 5th roadmap that Kirk and EPRI have published together since 2003 and reflects the technology development needs that can support an evolving U.S. power sector that's impacted by several emerging trends driving innovation and investment decisions for new generation. Some of these trends include increase in low-cost domestic supplies of natural gas, slow and in some cases declining load growth and electricity demand, as well as the need for generation to rapidly adjust to cycling load demands with increased intermittent renewables on the grid. There are several technologies identified in the roadmap that address these trends yet enable a transformation in the way we use our fossil fuel resources. These include novel power cycles like those already discussed, the supercritical CO2 cycles, or key processes in those cycles that are designed to facilitate the capture of carbon dioxide at a lower energy penalty and cost than conventional methods. These processes are inherently more efficient, resulting in fewer emissions of both carbon dioxide and criteria emissions, less water use, and require fewer fossil fuels to produce electricity. The roadmap also outlines advances in carbon capture technologies designed to lower costs, and the development and testing of these technologies at test centers such as the Wyoming Integrated Test Center and the National Carbon Capture Center in Alabama. The roadmap also identifies research on breakthrough technologies to ensure out-of-the-box thinking or fundamentally new approaches for using fossil fuels are developed, and includes typical programs like those discussed by Dr. Aines. Many of the technologies identified in the roadmap are readying for pilot testing today, and a few are preparing for commercial scale demonstration. I also want to discuss a companion analysis conducted by Kirk and ClearPath Foundation with modeling provided by NERA Economic Consulting and Advanced Resources International that shows that there are significant economic benefits to the U.S. if the technology development outlined in the roadmap is undertaken under a wide range of scenarios. Our analysis projects up to 87 gigawatts of market-driven carbon capture deployment paired with enhanced oil recovery by 2040, resulting in a significant increase in domestic oil production and lower cost retail electricity rates, all of which contribute to substantial increases in annual GDP and are projected to result in over 800,000 new jobs through 2040. These macroeconomic benefits are described in more detail in my written testimony and a report summarizing the study that will also be released next week. While both Kirk and EPRI developed the roadmap, I just want to make sure it's understood I'm speaking only on behalf of Kirk today, and we're very pleased to support the House Science, Space, and Technology Committee efforts to explore next-generation fossil power technologies and to discuss solutions that will enable our nation to continue to responsibly benefit from the utilization of our fossil energy resources. Thank you for the opportunity to provide you for this testimony.
Thank you, ma'am. Mr. Beggar, you are recognized for 5 minutes.
All right. Mr. Chairman, members of the subcommittee, I appreciate the opportunity to speak to you today about our carbon technology efforts in Wyoming. My name is Jason Beggar, and I'm the Executive Director of the Wyoming Infrastructure Authority. The WIA is a state instrumentality tasked with promoting and assisting the development of energy infrastructure. Currently, our largest project is the Wyoming Integrated Test Center, the ITC, which is a private-public partnership between the state of Wyoming, Basin Electric Power Cooperative, Tri-State Generation and Transmission Association, and the National Rural Electric Cooperatives Association. We have also received various in-kind contributions from Black Hills Energy and Rocky Mountain Power. We cannot stress enough the importance of this private sector partnership, because we shouldn't be focusing on projects and technologies that the industry won't adopt and commercialize. While we believe there's an important role for the federal government to play in advancing technology, and we would welcome a partnership, not 1 cent of federal dollars has been utilized at this facility. The ITC is a post-combustion flue gas research facility located at Basin Electric's Dry Fork Power Station near Gillette, Wyoming. It is the largest facility of its kind in the United States, delivering up to 18 megawatt equivalent worth of scrubbed flue gas to researchers testing CCUS technologies. The power plant will provide flue gas to 5 small research bays, each capable of hosting tests up to about 0.4 megawatt equivalent, and a large test bay that can host 2 demonstration projects with a cumulative total of 18 megawatts. Last month, we formalized a 2-year partnership agreement with the National Carbon Capture Center in Alabama, which manages much of the Department of Energy's carbon capture efforts. In Wyoming, we don't want to duplicate the work already being done. We want to complement the other test centers by providing a place to scale up current research. Our goal is to test technologies to both capture and manage the carbon. One of the most exciting partnerships we've developed is with the X Prize Foundation. One of the best-known X Prize competitions was the Ansari X Prize, which awarded the first team to fly 3 people to space and back twice within 14 days. One $10 million prize spurred 27 teams to invest over $100 million in technology development. Eventually, Richard Branson licensed the technology to create Virgin Galactic, and today the private space travel industry is worth $2 billion only 22 years after the idea was created in the mid-90s. The Energy COSIA Carbon X Prize will award $20 million in prizes to teams that are best able to convert CO2 into other valuable products. Currently, there are 10 teams from 6 countries working in the final round to create things such as carbon nanotubes, methanol, building materials, fish food, and plastics. The 5 finalists testing at the ITC are working to convert CO2 from a coal-fired power plant, and there are 5 teams testing their technologies at a natural gas facility in Alberta, Canada. In April, Wyoming and the Japan Coal Energy Center announced a multi-year project which will test Kawasaki Heavy Industries' solvent-sorbent carbon capture technology. Stable, predictable, and adequate funding is necessary to commercialize these technologies. H.R. 5745 is a great start, but Congress may need to look at establishing other programs to scale up the most promising technologies. Finding funding to support a new program is always a challenge. However, the coal mine in the United States provides an opportunity. The majority of the coal mine in the U.S. is owned by the federal government and leased to companies. These companies pay a variety of taxes, including federal mineral royalties, bonus bids, abandoned mine lands fees, and gross proceeds taxes. Every year, the mineral royalties and bonus bids bring in about $500 million. With a 10-year authorization, half of that funding could provide about $2.5 billion to fund carbon management research. Technology is apolitical, and the U.S. can make its best and greatest impact by investing in technology development that can be utilized around the world. There is considerable debate over the future of coal within the United States. However, every credible energy analysis from the UN Intergovernmental Panel on Climate Change to DOE acknowledges that large amounts of coal will be used globally for the foreseeable future. Technology is the best way to ensure these countries have access to power, yet can meet environmental goals. I appreciate the opportunity to speak with you today, and will gladly answer any questions. Thank you.
Thank you, sir. I now recognize myself for 5 minutes. Dr. Aines, in your prepared testimony, you highlight the need for national labs and the private sector to work closely together to develop carbon capture, use, and storage technology. And just as an aside, in Port Arthur, Texas, my district, we have probably the largest carbon capture sequestration unit in the country that I believe was funded by the ERA. Went to the ground breaking or the ribbon cutting, probably 3 or 4 years ago, I guess it was. However, I want to point out it's the ultimate responsibility on industry, of industry to commercially deploy these technologies. So, in your opinion, when is the appropriate time for the fossil energy industry to take innovations from that lab to commercialization? And before you answer, do you have like a pipeline of information and research you're talking with industry consistently so that you're able to keep them up to date and then sufficiently or successfully hand that off to them? How do you do that?
We do it best when we work in partnership early on, which is why I mentioned this roundtable that we had where we brought industry in to ask them what they wanted to do. And we will be partnering with several of those companies to develop technologies. The concept of us developing and throwing it over the fence, as we call it, does not work well. We need to understand exactly what industry needs and pass it off at the time that they're ready to take it.
Right, and that's why I say not, that's why I say a pipeline of information. You want to keep them involved and keep them working. And I guess you work with some of the associations around that also are very attentive to this process, and they would be able to keep, their members involved, so that when we do get to that where it's economically feasible, viable, then you can hand that off. You have those relationships established.
Yes, sir. We try to develop those, but I have to say that is a major challenge to maintain those relationships because we need things to work on together to actually have a relationship.
No, I got you. What tools do the national labs and the nonprofit research institutions have in their toolkit, that make y'all better suited to conduct that early stage research in support of the innovative technology? How would you describe that toolbox?
We have a broad base of science and technology that we can use to look at the whole system. Rather than being an advocate for one particular technology, we like to say, what's the problem that needs to be solved? And then, somebody of the 7,000 scientists that work at my laboratory is likely to have a solution. If not, then one of the 17 other national laboratories. So it's important not to be just out there pushing a solution because we have one, but to work on the solutions that are required.
Right, and one of those tools we would hope, going back to my previous question, would be that you have robust relationships with industry, maintain those relationships and keep them interested. So that's a good thing. Lawrence Livermore National Laboratory, LLNL, what do y'all call it?
We call it Lawrence Livermore.
Maybe we should call it L's in L. Get you a new mantra, all's well and L's in L. And so a shorter name would be good. But y'all have supercomputers and tools like carbon capture simulation, innovative tool set, which provides end users in the energy industry with computational modeling tools for the development of carbon capture technologies. So how does L's in L, as I call it, make sure that academic or energy sector partners can access this research infrastructure and the technical assistance the lab can provide? How do you do that, and how often do they access it?
We have a mechanism called the CRADA, Cooperative Research and Development Agreement, which we use when working with industry, and we do those commonly. They are a little complicated to put together sometimes. The second thing that we do that is a new program that has been very effective is called HPC for Energy. That stands for High Performance Computing for Energy, and that's a program where the Department of Energy pays the staff at one of the national labs that has expertise to work with an industry problem. The industry compete to get their problems worked on, and then we partner to bring the correct expertise to that industry, and that's been an extremely effective way to bring our high-performance computing expertise to the use of industry.
Do you find industry from all across the country, or is it more sectionalized, if you will?
Oh, all across the country. It's a very competitive program.
Does the fact that y'all you're a nuclear weapons lab, does that hamper or help in that program?
I would say it's not a factor.
Not a factor? Okay. Well, I appreciate that. I'm going to yield back, and the chairman recognizes Mr. Mark Beesey.
Mr. Chairman, thank you very much. I wanted to ask Ms. Angielski a couple of questions. In your testimony, you described the challenges of attracting private sector investment, not only for so-called early-stage technology development activities, but for each stage of the path toward commercialization. I was wondering if you could discuss that in a little bit more detail, and also if you could just kind of provide a typical time frame from concept to commercialization, and what levels of investment and risk are private companies willing to take so they can deploy these sort of first of their kind technologies without any kind of federal support.
Certainly. The early stage research is at a point in time where technical risk is low as well as cost risk. And so basic research can typically attract both public sector and private sector financing, despite what might be long lead times, as you just outlined, for return on that investment. Typically, what we see for generation technologies, which are very large, capital-intensive baseload generation technologies, from concept to commercialization, it's typically taken anywhere from 15 to 20 years to actually get a commercialized technology from concept to commercialization. So it's a very long lead time to actually look at what all the scales of development are needed to actually have that technology be able to be operational in commercial practice and then adopted in commercial practice. So when we look at going from that fundamental basic research, the next step is to scale up to testing those technologies under what we call real operating conditions. And so that requires more investment. You're building equipment, and you need to actually spend time operating that facility under those conditions that you can get the operational test data needed to actually scale up and design for a commercial project. And so as we move through those stages of development and you scale up, it's going to be a significantly larger investment in cost, but yet, again, your timeline to that return on the investment is long enough that attracting both internal financing from companies as well as private sector financing can be somewhat difficult to justify, particularly if there isn't a market pull for the technology at that time. So that's essentially, from just a timeline perspective, but also part of the challenge in attracting that private or internal financing. It can be difficult to achieve, which is essential for the federal support to get those technologies actually tested and demonstrated and across the finish line.
Oh, thank you very much. I also wanted to ask you about the legislation that I'm working on that I mentioned in my opening remarks, H.R. 5745, a bipartisan Fossil Energy Research and Development Act of 2018. It helps bridge the gaps between what the private sector is willing and able to do on its own and what we really need to do to commercialize these technologies at a sufficient pace to meet our national and economic goals. Could you talk a little bit about that?
So I will say that H.R. 5475 or 5745, I'm sorry, is very consistent with the technology development programs that we have identified in the Kirk-EPRI roadmap, which is why we were very pleased to support the legislation. The legislation would authorize both basic research as well as pilot scale development testing and commercial scale demonstrations, which we see as critical and necessary for advancing these technologies up to commercialization. It would authorize carbon capture projects and accelerate those projects with the funding that's provided through the development or authorization of test centers like those described by Jason, both at a small pilot as well as Jason identified in his testimony at a pilot scale, which is necessary before jumping to commercial scale operation. The legislation also authorizes all of the technology development pathways that we have identified in the roadmap for new power systems, both transformational as well as other technology development efforts like high-efficiency materials, for example, that will be needed in order to support those new processes in the future. And then in order to fully address the reduction of carbon emissions, the legislation also authorizes carbon storage outside of utilizing CO2 and enhanced oil recovery or converting CO2 for carbon dioxide, but that will be really important in the future under any scenario in which we find ourselves in a carbon-constrained future. And so that's something that we've outlined in our roadmap as well.
Thank you, Mr. Chairman. I'm out of time. Yield back.
Thank you, gentlemen. Chairman Biggs, you're recognized for 5 minutes.
Thanks, Mr. Chairman. Again, thanks to all of you for being here today. And Dr. Brun, can you please explain some of the environmental benefits of super clean CO2 power cycles?
Basically, what you're doing here is you're providing a power cycle that's more efficient, and that's the first generation of supercritical CO2 plants. So just by a 3 to 5, sometimes 7% efficiency of a power plant, you're really reducing all criteria emissions by that percentage. The next generation of supercritical CO2 plants, which is really what we're looking for, is the holy grail of supercritical CO2, is oxy-fuel combustion. And that leads to a potential for a completely carbon emissions-free power plant, because what you end up doing is you are getting a 100% concentrated stream of CO2 at the end that's already pressurized, and so it's ready for sequestration. So the short-term goal is really an incremental improvement of efficiency and obviously reduced power cost and cleaner power. The long-term goal is completely carbon-free power plants.
It leads me to wonder, you must see a path to that. I mean, obviously you don't know all the technologies and answers, but you do see a path to the Holy Grail, I guess.
Yeah, we have a development roadmap, and that's coordinated between the different industries. And it's really been a very, very positive collaborative industry, academia, and government process over the last 8 years. We've really moved the technology forward over the last 10 years. Normally in the power generation side, it takes decades to move any technology forward, and we've really moved supercritical CO2 in the last 8 years from concept to power plant technology. So we similarly have a roadmap to get ourselves to oxy-fuel combustion, which is that next level of supercritical CO2 plant. I would say we're about 5 to 10 years away from that, and there needs to be continued aggressive funding, both from industry and from government, to achieve that. But right now, I think there is a clear path toward that.
Okay, so when you talked about, in your testimony today, you said we're on the verge of commercial viability. Where in that path do you see commercial viability coming in if we're, what, 5 to 10 years away from oxy-fuel combustion?
Right. It depends on what type of oxy-fuel or supercritical CO2 plant you're looking at. So supercritical CO2 plants at the lower temperatures, for example, for waste heat recovery, those are now commercially available. They have been, you can now go to General Electric, or you can go to other companies and say, sell me one, and they will sell you one. That was not the case 3 years ago. That was certainly not the case 8 years ago. We're trying to get to that same level on other technologies, like, for example, concentrating solar power, higher temperature supercritical CO2, so more for fossil-type applications, maybe in the next 3 years. Oxy-fuel combustion is probably going to take 5 years. So some is already commercially available, and some is not. And so there is a development path that we need to follow, really toward higher temperatures.
And so what regions of the country or what areas do you see benefiting the most from this technology?
There's really no limit there. This is widely applicable. The nice thing about supercritical CO2 is that it's siteable anywhere, and it doesn't have any water requirements, and that makes it really siteable in places where there is, where you have to have access to water.
Like Arizona, I'm thinking.
Arizona's fine.
Very good. Thank you. With that, I yield back, Mr. Chairman.
Thank you.
Thank you, sir. The gentleman from California is recognized for 5 minutes.
Well, I thank the chairman. I thank the witnesses. I enjoyed your testimony. I especially thank Mr. Aines and Christy Schumer from Livermore Labs. I've been there many times. It's right side of my district. I appreciate the work that you're doing over there. I've often implored my Republican colleagues to embrace carbon sequestration, especially if their districts mine carbon or burn coal or burn coal. It might help them in the long run. Is there anyone in the panel that disagrees with that sentiment? I see heads shaking that they agree with my sentiment. Thank you. Mr. Aines, you spoke about the need to transfer within the DOD about carbon capture from coal-fired to gas-fired systems. How do you suggest that we accomplish that?
From the DOE.
What did I say, DOD?
Yes.
Thank you for the correction.
The most important thing is to engage partnerships like what's going on in Wyoming so that the researchers get to work together with industry.
Well, that was simple. So I also appreciate what you said in your written testimony about the Paso generating facility in Bakersfield. It's near an oil field that's well suited to CO2 storage. Can you talk more about the policy considerations such as the 45Q credit and California's low carbon fuel standard for incentivizing that development?
The issue with carbon capture today is that no one can afford to do it. And so we need incentives to help these first movers get the ability to have a business that's going to make money doing it, just as we did with wind and solar when we first started. Mount Poso is going to take advantage of two of those, the 45Q tax credit, and within California, if you're making a transportation fuel, the low carbon fuel standard, as of last week, was trading at $185 a ton of CO2. So when you combine those two things together, $220, $230 a ton is something that people are absolutely looking at to make real money, and we expect that places like Mount Poso and places like the ethanol refineries within the central part of the country are going to jump on these opportunities to make money while controlling carbon dioxide.
So do you think that carbon capture and sequestration can be viable without a price on carbon in the long run in the nation? Also, Ms. Angielski could answer that question as well.
I think that it's a difficult task that is going to require prices like those mechanisms that I just discussed. I don't think we're ever going to make enough money just from selling the CO2 to do all the carbon management that we need to do.
Thank you.
I am not sure that from Kirk's perspective, commenting on whether regulation is necessary or not is not a position that we take. I think what we take is the position that Dr. Aines just described, which is improved technology will be needed, particularly for deployment of carbon capture in the power sector. It right now is the differential between the cost of capturing the CO2, which is where the 45Q credit comes into place to help reduce those costs and actually incentivize the deployment of these technologies in the power sector as well as in other industrial applications like the ethanol industry, as you just described. However, right now, those credits are not enough to offset the production of CO2 in the power sector. So that's where we believe that improved technologies through the public-private partnerships with the Department of Energy will help to reduce the cost of applying those technologies in the future. And that will be needed in addition to some of these incentives like 45Q to overall deploy the technologies in the market.
Well, thank you. I'm really interested in the technology, this high-pressure carbon technology, super pressure. Can you describe a little bit, Dr. Brun, where that fits in with the Carnot cycle? Where does the alum cycle fit in with the Carnot cycle?
If you're talking the alum cycle, I mean,
We're talking about the alum cycle with
yeah,
high pressure.
that's one of there's the host of supercritical CO2 cycle. Supercritical CO2 really just replaces either steam or water in the cycle. So there's a host of cycle. They're all called Brayton cycle. The Carnot cycle is kind of like the idealized cycle. Fundamentally, the supercritical CO2 cycles, the host of cycles, one of them being the alum cycle, and that's a very promising cycle, by the way. They all end up benefiting the efficiency of the cycle and the power output of the cycle because supercritical CO2, it's really carbon dioxide at high pressure and high temperature, is a much better thermodynamic fluid than steam or air. There's nothing wrong with steam or air. We've been using it for 250 years. It's good. It's abundantly available, obviously, but carbon dioxide is just from a thermodynamic perspective a better fluid.
With the chairman's indulgence, I mean, you're going to have carbon dioxide left over eventually. I mean, you're going to have to do something with it.
Right.
And is it remain pressured after the cycle? You can still
you can
utilize use it somehow.
Yeah, the beauty of it is that you don't have to do any flue gas or pre-combustion cleanup, right? All this where you need to do something to get the carbon dioxide out of the flue gas, out of your exhaust. You don't have to do that because what you're getting out is 100% CO2. at pressure already, so you don't have to compress it either, so you don't have that compression penalty. So you're ready to take that CO2 and do whatever you want to do with it, sequester it or use it for advanced other products. That's the nice thing about that cycle, whereas in other air cycles, you have to take the CO2 in the stack emissions out of the air at a low percentage, which is expensive. In the CO2 cycle, in the oxy-fuel cycles, you don't have to worry about that. You get pure CO2 already ready for sequestration.
With the chairman's gratitude, I yield back.
Absolutely. I think in that instance, Dr. Brun, I don't want to continue this because Mr. Rohrbacher is straining at the halter over there. It's the infrastructure to get that pure CO2 to where it's needed. Isn't that the challenge?
Yes, that's an additional challenge. Obviously, you have to do something with the CO2 once you have it, right?
Yeah.
And so you're still going to need some pipelines. You're going to have to inject it somewhere into salt domes. All that is additional cost. There's obviously been quite a bit of work in those areas, but yes,
Thank you.
there's.
And I thank the gentleman from California. That was a great exchange. The other gentleman from California, Mr. Rohrbacher, is
Thank you very much, Mr. Chairman. It's been a very interesting discussion, and let me know I'm not an engineer, so some of the things I'm still trying to come to grips with of how we are accomplishing the various output that based on the input and what's in between there. I'm not really sure about some of the engineering, but the basic motive that we have, supposedly, or the basic motive behind much of what's going on about CO2 is based on the theory that CO2 is a major factor in causing our planet to get hotter and hotter. I don't happen to agree with that. I've talked to a lot of scientists who believe that premise is not correct, that ice cores, looking back at the ice cores from ancient times to now, actually has the planet getting hotter, and then there's more CO2 being created. I'm not going to ask you what your beliefs are on CO2 making the planet hotter. Let's just accept that today, the discussion today is based on, okay, there's CO2 that's being produced. Can we do something that is beneficial to mankind, even if you do not believe that CO2 is causing the planet to get hotter? And that discussion, I think, is very important for all of us to make, and we're very happy to have you here to help direct that discussion. In my own area in Orange County, we have a company called New Light Technologies. Are you aware of this company? I'm very proud of these young men who were surfers and went off to Princeton and got educated and realized that there was a potential for getting something out of the air, straight out of the air, that would be of value. And they have just opened up their first $50 million production site after spending years of perfecting it. And let me just note for the record here, it's New Light Technologies, and they are taking carbon dioxide and methane emissions right out of the air and producing high-quality plastic that is actually at a lower cost than the current method of producing plastic, and the plastic that they are producing has biodegradable properties that make it even more important, because whales that are eating plastic bags, we know that's bad. We know in fish, another ingestion of plastic is actually harmful for the environment. These kids are taking that CO2 out of the air and the methane out of the air and producing things that are cheaper and better. And so I think that's a formula for progress. And so whatever we do, we need to make sure that actually there is not just the benefit of keeping the planet from warming, but instead other benefits that go with that. Now I'd like to talk about that. I'd like to ask about whether or not, when we're talking about the Colorado, are the Wyoming projects and that are going on, or we have Well, let me talk about the scrubbers first and all what you presented for us, Dr. Brun, was very complicated. And again, I was trying to get a non-engineer to understand this. In the end, are you coming up with a product that actually is going to be cost-effective, or is this going to be an enormous cost?
No, all the models are predicting that it's cost-effective. And what's important here is that this is not done in a vacuum. We are working with industry. We're working with all the major power players in the United States and companies like General Electric and others that are investing significantly of their own money. So they're not just taking DOE money to develop this technology, they're investing their own money. And so they're clearly seeing commercial viability in that technology, otherwise they wouldn't be pursuing it.
So this is actually would be economically viable in and of itself?
That is the aim.
Okay.
Yes.
Dr. Aines, in your prepared statement, you mentioned the potential growth for using carbon for manufacturing in industry. And with both carbon dioxide and natural gas will be the main inputs for industry. When you think about natural gas and both carbon dioxide and natural gas being used as inputs for this, so why do we need to then have tax benefits and R&D funding for all fossil fuels if indeed we're just talking about the natural gas and carbon dioxide?
I can't answer that question in detail. I look to the future and I see that industry is very interested in using natural gas because of the simplicity and the cleanliness, but mostly the simplicity. And it's lower cost for them, and so that is where the direction that a lot of industrial movers are going.
Well, when it comes to CO2, and I drove across the country with my family a year ago, and one thing that was interesting for my kids was to see all of these fields that were covered with plastic and machines pumping something into that plastic with the different plants like tomatoes, et cetera. And my kids were very surprised to find out that they were pumping CO2 into these big coverings of agricultural products. Is the end situation there, we're utilizing CO2 for something that's positive. We get more food out of it. Is that so? Isn't this not an example? Is there more examples like this that we could have that we're using CO2 that will, in a way, benefit, like our friends are making plastic out of it? Are we going to see more of this? And maybe you have some examples specifically of how CO2 will be used to have other uses that are beneficial?
That's a great example. And another example that I would point to is the addition of carbon dioxide to cement and concrete, which I know of about 20 companies that are pursuing this. And the major advantage there is it makes the concrete stronger. And so you can use less of it, you can have a more efficient structure, and it's a terrific combination of having a better product and using the CO2 that we want to keep out of the air.
So we don't have to really agree on whether or not global warming is caused by CO2 to be very interested in this whole concept of science research and expanding the use of CO2 in a positive way.
You don't. You just have to agree and yield back.
Thank you.
Okay. All right. The chair now recognizes the gentleman, Mr. Tonko, for 5 minutes.
Thank you, Mr. Chair, and thank you to all of our witnesses for being here today. This is a critical topic because a modern society needs energy, and the only way we are going to meet our energy challenges are through investments in research and development. We often hear about the need to reduce government spending, and while that is certainly important, we cannot lose sight of the vital role that government plays in investing in innovation. The federal government must be an active partner with universities, with independent laboratories, and certainly the private sector. The only way we're going to meet our energy challenges are through investments in research and development. Having an R&D portfolio that covers the spectrum from basic sciences to technology development, testing, and deployment greatly augments the work being done by the private sector and in our university communities. Sustained support of these efforts is essential to lowering costs and improving performance of energy technologies. And when it comes to a national energy policy, there are so many areas that we should be further discussing, including battery development, storage, alternative energy, grid investments, energy efficiency, and innovation, and how we generate and transmit and conserve power. This committee should be looking at how we can invest so that our nation can have the best options to choose from to ensure that we protect our nation by addressing our national security and our public health and our nation's economy. I fully believe that across the field we need to develop technologies to reduce our carbon footprint and to increase efficiency in all areas, which is why I'm so proud of being a supporter of a bill to make gas turbines more efficient. Efficiency must be our fuel of choice, especially for fossil fuels. The gas turbine R&D bill, which I have worked on with Representative David McKinley, would authorize DOE's Office of Fossil Energy to carry out a multi-year, multi-phase R&D program to improve the efficiency of gas turbines used in power generation systems and to identify the technologies that ultimately will lead to gas turbine combined cycle efficiency of some 67%. This includes high-temp materials, improved heat transfer capability, manufacturing technology required to construct complex parts, advanced controls and systems integration, among other topics. And expanded government investment in research of gas turbine technology will lead to more American jobs, increased American global competitiveness, and reduced greenhouse gas emissions. So for all of our witnesses, how important do you think it is that we use our fossil fuels more efficiently if we continue to rely in part on them? Anyone?
I'm happy to answer. I think historically we've seen the benefits from improved efficiency in both gas turbines through natural gas combined cycle systems as well as coal-fired generation. And with every percentage point in improvement, we see a significant reduction overall in emissions as well as fewer fossil fuels being needed for that same amount of energy output. So it's very, very important.
Mm-hmm. Anyone else? Thank you.
Yeah. Oh. Mr. Chairman, Congressman, completely agree. You know, if you look back at the power plants that, this generation of power plants that have been retiring in the last few years that were constructed in the 60s and 70s, you had maybe a 30% efficiency factor. Today's power plants, and look at the Turk facility in Arkansas, which is super critical. It's up over 40%. So one thing that if the U.S. wanted to improve efficiencies and emissions today is you would find a way to build more of those supercritical Turk plants and close down the older plants, because efficiencies do matter and they do get us there.
Oh yeah, they address the amount of electrons we can save and the dollars we can save. So yes, sir, Dr. Brun.
Yes, I think gas turbine development is a really wonderful example of how you have a collaboration between academia, government funding, and industry, specifically GE in the United States and Westinghouse before, where you've taken a technology from after World War II, maybe in the 30% efficiency, to now we're talking 67% efficiency, which is by far the highest efficiency power plant technology that's out there. That's higher than anything else. And that's been dramatic. Even over the last 20 years, we've gone from about 55 to about, right now we're probably at 63, 64, but we are aiming for that 67%. So that research has been fantastic. And every percent that you save is 1% less CO2.
Right.
And it's 1% less fuel burned, and so that's been very effective research. That's been a great collaboration between industry and government and academia.
Right. It's hard to believe that there are think tanks out there that fight this effort to offer these challenges, develop these goals, and reduce the pollution, the carbon pollution. But they're there, and it's a force we have to work against. So with that, I thank you all for your input, and I yield back, Mr. Chair.
Thank you, Ms. Tonko. And the gentleman from Texas, Dr. Babb, is recognized for 5
Yes, sir. Thank you, Mr. Chairman, and I appreciate all of you being here today. Very, very interesting. Mr. Beggar, can you please describe the misconceptions that many people have of coal and why technological innovation can help clear up some of these misconceptions? If you would elaborate, please.
Mr. Chairman, Congressman, one of our biggest goals. I mean, the reason why Wyoming is involved in this is to figure out how can we ensure the long-term viability of a natural resource the state has. You know, a third of Wyoming's tax revenue is directly dependent upon the coal industry. The benefits of coal are pretty evident. It's the reason why the country has been using it for years. It's why China's using it, why we see these industrialized nations using more and more of coal, is it's reliable, it's stable, you can put it on a pile somewhere, you don't need a pipeline. It is a very great fuel for beginning an energy industry. And so I think our challenge now is how can we use that understanding societal's drive and demand towards lower carbon standards. You know, in the past, you know, nobody talks about acid rain anymore. It's because we developed scrubbers. The smog, you know, you see those old pictures from Pittsburgh and, you know, Detroit 50 years ago. We don't have those sort of things anymore because we developed, you know, bag houses and electrostatic precipitators. And so Wyoming's approach is, let's look at climate change as a political, or excuse me, as an engineering challenge, and not a political football, because industry time and time again has shown that given enough time and enough resources, we can engineer a solution and find that win-win. You know, let's remove CO2 and we can find an economic incentive to do so. That's great.
I appreciate that. That's very fascinating. And being from Texas, my district is over on the east side, where we produce a lot of natural gas. And yet 60% of our electricity in my district comes from coal-fired plants. Thank you very much. Dr. Aines, your research, in your prepared testimony, you mentioned the carbon economy and the future potential for growth and utilizing carbon as an input for manufacturing or industry. Both carbon dioxide and natural gas will be the main inputs to produce products from a carbon economy. Why is it important to have fossil energy research and development funding focus on all fossil fuels?
There are many options needed in an economy as large and diverse as ours, and we simply can't afford to pick winners. It's certainly not my job to pick winners. It's my job to deliver solutions, and that's why we need research across the entire gamut.
Thank you very much. And Dr. Brun, in your opinion, how quickly, unless, if you've already spoken about this, stop me, but I don't think you have, will supercritical carbon dioxide power cycles begin to replace traditional steam and air cycles? And could investments by the energy sector in supercritical carbon technology help us to continue to take advantage of our abundant and affordable fossil energy?
Yeah, I think we can see on the low temperature waste heat recovery side, we can probably see something in the next 3 to 5 years. Obviously, there's hundreds and hundreds of power plants, so it's not just an easy replacement. But I can foresee in the next 10, 15 years quite an impact from supercritical CO2 in replacement of, especially of steam cycles. On the air cycle, that's going to take a little longer, but probably 10 to 15 years. Okay. The technology is moving fairly fast there.
Yeah, glad to hear. And Ms. Angielski, can you give an example of carbon capture, utilization, or storage research through investments by fossil energy industry that could lead to an advanced carbon-based technology?
There are several that were discussed here today. So certainly the supercritical CO2 cycles. We identify several technologies in our roadmap, including pressurized oxygen combustion, which was described here today. We have some carbon capture technologies that are looking for testing right now that once tested could actually begin to have commercial offerings available. So there are a suite of technologies which from our perspective is very important to make sure that we have a diverse portfolio of technologies and that we're not just picking winners as already discussed. Right. But there are several technologies identified in the roadmap that are readying for that testing to be able to then take that piece of paper to a financier and say we can offer commercial guarantees. So.
Thank you, and I yield back, Mr. Chairman. Thank you.
Thank you, Doctor. The gentleman from Alabama, Mo Brooks, is recognized for 5 minutes.
Mr. Chairman, I'll defer.
Then the other gentleman from Alabama, we've got both of them here today, is recognized for 5 minutes. Mr. Palmer.
The one who will not defer. Thank you, Mr. Chairman. This is very interesting to me. I've worked for 2 engineering companies prior to running a think tank for 24, 25 years. I worked for Combustion Engineering and the Environmental Systems Division. We built, I see Dr. Brun nodding his head, we built scrubbers, precipitators, bag houses, and I just was wondering, on the latest technology, how effective are we at capturing CO2 right now, Dr. Brun?
Depends on how concentrated your stream of it is. If you're doing flue gas, I mean, you can capture 100% of it, right? I mean, it's technically viable. It becomes a cost issue. It's easier to, the more concentrated your stream in your flue gases, the easier it is to capture it. That's why we're pushing for the oxyfuel and supercritical CO2 type cycles. But you can certainly remove CO2 from the flue gas of a combined cycle plant. The only problem is it is at a low percentage, and so you have to scrub a lot more gas to get the CO2 out. But even there, you can remove 100% of the CO2. It just becomes a cost of electricity issue and how much cost you want to add to your cost of electricity. So the technology there, in that sense, exists, and it is just a question of cost.
One of the reasons I'm asking this is that when it comes to fossil energy, most of the time when we're talking about capturing carbon, we're talking about coal. But there are uses or potential uses for capturing CO2 for unlocking oil resources from shale. And we've got the Green River Formation. Are you familiar with that?
No, I'm not.
Green River Formation, and I have a GAO report, which was part of a committee hearing, I think in 2012, that got very little attention in the media. ABC News reported on it. But the Green River Formation holds 3 trillion barrels of recoverable oil. That's 3 times what the entire world's used in the last 100 years and 5 or 6 times the known reserves of the Saudis. It's just half of it would be more than the known all of OPEC combined. It's about half of it, 1.4 trillion, is the more recoverable, the richer deposits. But in your research, do you see the potential for using captured carbon for releasing or having access to such oil deposits?
Yeah, so I think using CO2 for enhanced oil recovery is certainly a recognized usage of carbon dioxide, and the combination of oxyfuel combustion plants where you get CO2 out and then you inject that at high pressures into the formation to get enhanced oil recovery is something that has been discussed by many oil companies. I've given presentations on the topic, actually. It is certainly viable technology for you.
But is it economically viable? Is it a cost?
Yes. It is economically viable, and it depends on your formation, it depends on your application, but there is certainly applications right now where it is economically viable, yes.
Do the Chinese or the Indian government do anything in regard to carbon capture?
The Chinese are doing quite a bit in that area, and maybe you can answer that too, but
yeah, any one of the panel, if you know the answer to that.
Yeah, the Chinese are very active, but you may have more information.
Yes, the Chinese are, in fact, the most active nation in the world in this area, doing large demonstrations and developing their own technology. The Indian government has done very little to this date.
And the Indian government is the fastest, the Indian economy is the fastest growing economy in the world, and they're doing quite a bit of building in regard to coal-fired power generating facilities. Is that accurate?
They are still building coal plants. It is decreasing there. They are building more renewables now than coal.
Good. Mr. Beggar, in your testimony, you mentioned partnership between the Wyoming Integrated Test Center and the National Carbon Capture Center near Wilsonville, Alabama. That, by the way, is in my district. Can you give us a little more detail about the work that ITC intends to do through this partnership?
Sure. Mr. Chairman, Congressman, The way that we see our role is complementing the work that National Carbon Capture Center, NETL, and the other labs have done. And a few years ago, when the state was looking about how to best get involved, and through the course of about a year and a half of reviewing critical gaps in testing infrastructure, what we recognized is that there are a lot of places to do small testing, like the National Carbon Capture Center on the backside of that coal-fired power plant. They can test up to about 1.5 megawatt size projects, but utilities needed to see something larger before making that leap. And up until now, really the only way to do that was a one-on-one relationship between the technology developer going to a utility and asking to basically cut a hole in the side of their power plant and access some of their flue gas. And as you can imagine, they were pretty reluctant to do that unless there was a long-standing relationship. So what we've done with that facility is sort of create the infrastructure there, a plug-and-play system. And so what we would like to see is the most promising technologies that make it through there be that sort of graduate school for them to come and test. And another area is access to all the incredible resources. You know, over years at Wilsonville, they've developed incredible institutional knowledge, engineering skills, and so having the ability to basically access their lessons learned and their best practices can hopefully help us prevent making those sort of same mistakes.
Well, this is all fascinating to me, Mr. Chairman. I, as I said, worked in engineering and environmental systems, and my brother-in-law worked for Southern Research and was an expert in scrubbers and bag houses. He traveled all over the world. I would love for him to have been here. He probably would have had some better questions than me. With that, Mr. Chairman, I yield back.
I thank the gentleman. The ranking member from Texas is recognized for another question.
Thank you, Mr. Chairman. Ms. Angielski, you know, as you know, and you've seen it on the news, the current administration has strongly opposed practically any regulating of greenhouse gases. And many, including the president and our former EPA administrator, have publicly questioned the validity of the broad scientific consensus on the current and growing threat of climate change. So in this context, please help us to better understand why are there Carbon Utilization Research Council industry members like Peabody, Arch Coal, and the American Coal Council so supportive of developing carbon capture, utilization, and storage technologies that may ultimately impact their profits if they're ever required to deploy them? If you could kind of help us understand that, I think it would really go a long way.
Sure. Well, as indicated in my testimony, there's growing international use of all of our fossil fuel resources. And as a result of that, there's growing international consensus that we will need to do something to reduce the carbon footprint from the utilization of fossil fuels. That's the position that we take when we look at evaluating technology development needs, both for today as well as what we're going to need in the future. As a result, as I mentioned earlier, a lot of that focuses on the ability to reduce emissions of CO2 and carbon dioxide. I think what's equally important about that is that many stakeholders, not just industry stakeholders, but also those in the environmental community, also share in that consensus, which is we recognize the growth in these fuels and we will need to invest in these technologies in order to achieve any global climate objectives. At the same time, we've also heard that there's both environmental benefits from investing in these technologies as well as economic benefits. And that's also another perspective that we take. When you look at these environmental benefits, for example, lower cost CO2 will be needed for enhanced oil recovery in the future. We have less and less CO2 coming from natural sources that are currently mined and used for producing more oil from our depleting oil fields in this country. So a lot of the oil companies in this country are looking to power generators for those large volumes of CO2 coming off of fossil fuels to be able to use that in enhanced oil recovery. So we're looking at that as a market opportunity as well. If we have, as was described earlier, maybe a waste product and CO2 being vented in a flue gas stream, why not put that to good use and get some economic value out of it while also producing more domestic oil and ultimately producing a low-carbon barrel of oil as well, which is important to recognize. So there's both tracks that can be pursued. I think over the long term, if under any future scenario, I think we share a view that we may be living in a carbon-constrained world, and we want to make sure that we have those technologies available to enable us to continue to utilize our fossil fuel resources and have them be competitive with all of the other low-carbon generation sources that are available to us today as well.
Mr. Chairman, I yield back. Thank you.
I thank the witnesses for their testimony and the members for their questions. The record will remain open for 2 weeks for additional written comments and written questions from members. The hearing is adjourned.